Good afternoon, everyone, and welcome to the latest 2DCC webinar. Today we have Dr. Shan from Cornell University. Dr. Shan received her PhD in physics at Columbia University. She then went into faculty at Case Western Reserve, then faculty at Penn State, and is now faculty at Cornell University starting in 2018 as a full professor. Today, the talk is going to be on 2D moire quantum materials. Please go ahead, Dr. Shan.
Thank you very much, Carmen. So I'm going to talk about 2D moire quantum materials today, a little bit from a physicist's point of view as a platform for strong correlation, and of course also topology, but I probably wouldn't have a chance to get into the topic of topology. So what is moire? If you overlay two sheets of two-dimensional materials, in this case, a monolayer of tungsten selenide and a monolayer of tungsten selenide on top of each other with a small twist angle, you see this long scale interference pattern. And this pattern we call moire pattern. So when the twist angle is small, you can get a long period. So for a couple of degrees, you get this large scale pattern with this period on the order of 10 nanometer. You can also get moire pattern by stacking two different materials with slightly different lattice constant and a zero twist. So in this case, it's a tungsten selenide and tungsten sulfide monolayer. Because there's a 4% lattice mismatch, the moire period is 8 nanometer. And you can also do hydrobilayer with twist, so then this period will go down even more. So we call some materials moire materials, mostly for stacked semiconductors or semi-metals. So the pattern you saw here, on the large scale, it looks periodic, but if you look it down, they are quasi-periodic, right? But when the period is long compared to the atomic lattice constant, and when we are dealing with semiconductors or semi-metals, what I mean is that, if you look at the energy distribution in terms of a crystal momentum, you can find some pockets that, mostly energy dispersion is confined within some small crystal momentum range. So in that case, you can forget about, the atomic scale, and you can just think about electrons in this moire structure as seeing some periodical potential. So this is kind of a cartoonish version of what electrons see in that interface. And this is true only when we consider low energy physics. And so this is kind of the cartoonish picture for electrons in this periodic moire potential. And you can think about, each is like an artificial atom, but now the period is 10 nanometer, and the depth is on the order of 100 to 200 milli electron volts. So this artificial two-dimensional solid is different from the real solids. So real solid, the period is much, much smaller. We know it's on the order of, half nanometer-ish. And the depth there is about several electron volts. So this is the system we are going to study. I'm going to talk about in the rest of my talk. From single particle point of view, I have those artificial atoms, and you can think about adding electrons into those atoms. So for example, if I add one electron, it takes up one type of atomic orbital. And if I add more, you can have, SPD. And this way you can really build up your periodic table and do moire chemistry. And the system is highly tunable. And in this example, what we have shown is that just by gating, it's like a capacitor, like a structure, you can introduce, up to 8 electrons per atom. So every time when you add a new electron, it's like changing one element to another element. Right? So what makes us, a bunch of physicists excited about this new material platform is the strong correlation effects. So let me just give you a hand-waving argument why this is an ideal place to study a strong correlation physics. When we say something is strongly correlated, what we mean is that the Coulomb interaction energy is bigger than the kinetic energy. So if we just have some kind of 2D periodic structure, let's say the spacing is on the order of A, and then we can estimate the Coulomb interaction energy. It's going to be charge squared divided by distance and scaled by some dielectric constant of the medium, right? And we can also estimate the kinetic energy, which is momentum squared divided by 2 times the mass of the particle, right? And the momentum is inversely proportional to this period. So we end up with kinetic energy scales like 1 over distance squared. Then the ratio of Coulomb interaction energy to the kinetic energy is proportional to this product, mass times the period. So if we have a moire material with period on the order of 10 nanometer for a typical transition metal dichalcogenide, we are talking about mass on the order of half electron mass. You can estimate this ratio, it's on the order of 5, and that's considered big. And that tells us that the correlation, the interaction is important. And you can also look at this from different point of view. You can say, okay, that means the kinetic energy is small. When the kinetic energy is small in the electronic bands, we are talking about flat band. It's narrow. That means the kinetic energy is small, right? And as comparison, if you look at the real material, the period is on the order of half nanometer, and this ratio typically is very small. So you don't need to worry too much about, this correlation effect, or you need to engineer something, with localized charge, flat bands in order to see this correlation effects. So the importance of correlation in this twisted material has been predicted some time ago in those theory papers. And those papers also provide instruction how to create those flat bands in twisted bilayer graphene. And experimentally, this has been demonstrated a few years ago at MIT. So what's happening here is that if you put the 2 sheets of monolayer graphene at this magic angle around a 1 degree twist from each other, you have interlayer hopping and the interlayer hopping sort of comparable to each other. And in that case, you get a flat band and correlation becomes important. And later on, we also find interesting magnetic, superconducting, and many other interesting properties from twisted bilayer graphene and related graphene systems. And one of the very, very important features about the moire system is their high tunability. So the parameters of the system can be continuously, controllably tuned. So for example, I already mentioned the charge density. You do not need to do any chemical doping. What you need to do is put your moire bilayer, for example, between 2 gates, and you can apply a voltage, a few volts. You can load, each atom from 1 to I showed you up to 8, So the charge density is highly tunable. I mentioned about the depth of the potential, typically on the order of 100 to 200 millielectron volts. And this is controlled by the corrugation between the bilayers and also interlayer hopping. So you can use, the displacement field, the perpendicular electric field to tune this. So this is also quite tunable. And then the moire period is dependent on the twist angle, right? And recently, group at Weizmann demonstrated that you can put one half of the device on a tip of AFM and the other half of the device on a rotating stage. So you can rotate the angle, do your tunneling measurements. So at any arbitrary angle you can do. So you can change your moire period continuously. So this kind of a tunability and a controllability makes moire material a very attractive platform to discover new quantum states, and can also be used as quantum simulators. So this idea of quantum simulation was first brought up by physicist Richard Feynman. So in this case will be, if we want to study some complicated system, we can emulate it with another much simpler quantum system with parameters highly controllable, and you can tune and you can measure, but they are governed by the same Hamiltonian. And that way, by studying this well-controlled system, you can get the answer you are looking for. So the moire materials are pretty good candidates, for this type of applications. Okay, so after this brief introduction, I would like to get into what I will talk about, the progress made in my lab at Cornell. I will tell you a little bit about the building block of the moire materials we use. We'll be studying two-dimensional semiconductors, mostly transition metal dichalcogenides, compared to the twisted barrier graphene. We do not need a magic angle. Pretty much, any small angle can be magic. And then I'll give you a few examples to study strong correlation physics. First for electrons, and then I'll talk about the bosons. I don't have time to talk about topology. You can find more from this paper or from our recent review paper. Okay, so the building block of my favorite moire material is from this group, transition metal dichalcogenides. I probably don't need to mention this too much because I think, this is one of the material system that, Penn State colleagues have been studying very widely. So pretty much, you have this transition metal in the middle and chalcogen, sulfide, selenium, telluride on top and the bottom. So the structure is very similar to graphene, but now the A and the B sublattice are occupied by different atoms. The band edge of this class of material in the monolayer limit also occur at the K and the K prime point. So this is a simplified version of the electronic band structure of monolayer TMDs. We have very strong spin orbit interaction. So the bands, especially the valence band are largely spin split. But to conserve time reversal symmetry, when we change from K valley to the minus K or K prime valley, the spin also flip. So we have spin and the valley locking. So in other words, here we also have double degeneracy. Spin and the valley are coupled. So now we can isolate monolayer of, let's say, one type of TMD, WS2 or WSE2. And we determine the crystal orientation by doing nonlinear optical measurements. And once we know the crystal orientation, we stack them. And this is, the cartoon version of how to get this semiconductor moire heterobilayer. And we can then put those into two gates. So in this case, will be hexagonal boron nitride gate dielectrics and field layer graphite as gate electrodes. And you can apply two voltages, top gate voltage and a bottom gate voltage. So we have two parameters which can control two things independently. One is the total charge density in this moire. And we are going to use the unit of moire density. So if we go back here, you have this moire unit cell. So we have 1 particle per moire unit cell. I call the filling factor equal to 1. 2 particle per moire unit cell, I will call it filling factor 2. Okay. So the two gates can control the filling factor and also can control the outplane electrical field across this bilayer. And you will see this is useful for tuning the depth of this moire potential. And this is a photograph of one device. And you can see that the effective moire heterobilayer is just the inside this near rectangular shaped pattern here. And then you can add electrodes, make contacts. This way you can do transport measurements, and you can also shine light from top and read out the optical response. Okay, so I talk about stacking the two layers together, right? So effectively, you are folding, this Brilliant zone for each bands into many, many smaller ones. And because, this moire period is 30-ish times larger than the atomic period. So we are just looking at a very small fraction of this original Brilliant zone. So we are looking at a mini moire Brilliant zone. So this is just a percent of original one. And you can see that, near that top, I do have something very flat, right? And this is the way to get a flat band. Also, I can play with the band alignment of two different materials. So I can make the other material, the bands further away from the Fermi level than if you just concentrate on the first moire band here, the other one is far away. So this can be quite isolated. So if we just focus on the first moire band, you can project this problem to something called a Hubba model. And that was shown by Alan McDonald's group a few years back. And in our case, the lattice is triangular. So to make life easier, I'm just drawing a square lattice. So what this Hamiltonian includes just the two terms. We count for electron hop from one side to another side, and that's this hopping integral T. And to take a Coulomb interaction into account, we only take the first term, so U, and that's the energy you need to pay by putting two electrons on the same site. So this Hubba model is one of the most important models in condensed matter physics. It studies electron correlation in narrow energy bands, and first proposed in the 60s. And it's important because the model is thought to describe important problems such as high TC, quantum magnetism and also describe important quantum phase transitions such as Moore transition. It's a metal to insulator transition. So let me just say a few words about this transition. So I told you about those two terms, right? The hopping term tends to delocalize electron, and this U term, if you have full filling, it's like one particle per site, then electrons you don't want them to move, because when you move, you have a double occupancy and it will have this energy U to pay. If U is big, this is not favored. So we know that in the limit, when U is very small, then we just have half filled band, and this is Fermi liquid, right? But when you make U very big, as I said, you have to pay this penalty to make electron move, and then this is the gap, So if you make it a hop, then this is extra energy you need to pay. So instead of being Fermi liquid, this is an insulator, and it's a Mott insulator. So in the Mott insulator, if you look at this ground state, you just have, localized charge at each site. They don't move, right? But the low energy, this excitation of the ground states now are pretty much determined by the spin-spin interactions. And the favorable configuration will be something like that. It will be antiferromagnetic interaction. So you can think of like this electron can virtually hop over and hop back. And this interaction strength is proportional to T square over this U unit, and it's antiferromagnetic. So at some intermediate interaction strengths, U over T ratio, we should have transition from metal to insulator. And this is something, pretty well known called the Mott transition. Originally, when Mott proposed this question, the thought was that, at this transition, both charge and the spin go through some change. And, the charge, this small transition could be sort of influenced by the magnetic order change. So at that time, people, including Mott, thought, this should be abrupt, because it's very hard without doing fine tuning to have those two occur at the same point, right? So this still is kind of an open question about this transition, whether it's abrupt or continuous. And in real material system, it's hard to tune, just the interaction or the bandwidth. So next, I would like to show you a few examples, how we use the moire material to study this Hubba model on a triangular lattice. Before I do that, I would like to first talk a little bit about some new technique we developed at Cornell to study this type of a problem. If we talk about metal to insulator transition, of course, the best will be measuring, magnetic properties and measuring transport properties. And for those of us, who work with transition metal chalcogenides, that, those are semiconductors with large band gap. It's not trivial to have good electrical contacts to those materials. Although we are getting better to develop a good electrical contacts, but often still this is a problem. So we came up with this technique, which utilizes the optical properties of monolayer transition metal chalcogenide. So this is something pretty well known already in the field, that electron hole are strongly bound in transition metal chalcogenide. They form excitons, and exciton binding energy can be on the order of a fraction of electron volts. And you can observe not just the fundamental exciton state, you can also observe the excited exciton state, 1s, 2s, and 3 or 4 till at some point you hit the band edge. So that's the continuum. We also know that, the dielectric screening is small in monolayer setting, let's say, in some environment. So the electrical field line that are responsible for electron hole binding are mostly outside this monolayer materials, like what I'm showing in this cartoon. So the binding energy is very sensitive to the surrounding dielectric material. Therefore, if I bring in a metallic state next to my monolayer of TMD, I will see a very strong screening effect, and that will make the exciton binding energy small and also make the absorption weak. But if I bring in an insulator next to my monolayer TMD, I would expect the screening effect to be small, so the binding energy will still be big, and the absorption of this exciton will also be strong. And we also know that 1s exciton is relatively small, but if you go to 2s and a 3s, the ball radius just increases very fast. So we decided to use this as a probe of what's going on in this 2D electron gas. So this is going to be my moire. So let me just show you the device structure. So this is my moire, which I want to study. In this case, it's angle aligned tungsten selenide and tungsten sulfide. And I put the 2 gates, top gate and the back gate, to control the doping density and outplaying electric field, right? But then in order to measure what's going on when I put a charge or apply electric field to this layer, and I bring in a sensor, which is 1 or 2 nanometer away from my material, and separated by hexagonal boron nitride spacer. So I make sure my sensor is charge neutral. And because the distance here is about, a couple of nanometer, and I told you about the size of those exciton excited states, it seems that 2s exciton will be most sensitive to what's going on in the sample layer. 3s, 4s, they will be much weaker in terms of absorption strength. So let's just take a look. So now I'm showing the spectrum of 2s sensor, the 2s exciton absorption in my sensor layer, while I'm changing the doping density in my moire heterobilayer. So if I turn on positive voltage, that means I'm doping electrons into the moire. And if I use a negative voltage, I'm doping the moire with holes. Okay. And, this is kind of a pretty picture, but it has lots of structures. So I want to point to a few features. So the background at some lower energy, so it doesn't have much. So this pretty much means, like for most like a metallic states, my 2s sensor exciton are dielectrically screened quite a lot by what's going on in the sample. But then on top of this background, I have some strong absorption. So that means the screening is weak at those, blue spots. And that means those are insulating states. So when you see strong 2s absorption, that means the state in the sample is insulating. And I also convert the voltage to filling factor. So 1 means 1 electron per moire unit cell, and 2 means 2 electron per moire unit cell. So at 2 particles per moire unit cell, this is obvious why it's an insulator, right? Because I completely fill 1 band, and this is a band insulator. But at a filling factor 1, I got also an insulator, which should be metallic in the absence of electron-electron interaction, but I got a very strong, insulating state. And this gives me a hint that interaction is very strong, and this state is likely a mod insulator. And it's the same thing happening on the whole doping side, so this could be a mod insulator, and this is a band insulator, right? So, and this also has been verified by doing transport measurements. So what I'm showing here is just the resistance as function of doping and also at different temperatures. So when we cool down sample more and more, you can see, those resistance goes up, really behaves like an insulator. But to really verify, the mod insulating state, we have to look at the magnetic properties, because that's what defines the nature. So we also measure the magnetization as a function of magnetic field. I'm not going to get into the detail how to measure this. It was done optically. So you can see here, magnetization increases when we increase magnetic field, and then above like about 1 Tesla, it saturates. But at the small field, it's linear. And what this slope actually is the magnetic susceptibility, it's just the magnetization divided by magnetic field, right? So we can also do temperature dependence of this, plot this as a 1 over magnetization, magnetic susceptibility as a function of a temperature. If it's local moments, then at high temperature, the magnetization should follow Curie-Weiss law. Which just says, 1 over chi is proportional to T minus some theta. It's a straight line. And if you extend the straight line, we hit some number. Sorry, there's a typo. This should be -1. So this Curie-Weiss temperature is -1 Kelvin. So negative Curie-Weiss temperature says it's anti-ferromagnetic interaction. If it's positive, that's ferromagnetic interaction. And it's on the order of, less than 0.1 milli-electron volts. And this is consistent with the super exchange mechanism I talk about. It's proportional to hopping integral T squared divided by on-site Coulomb interaction. And we know what T and what U are from calculations. And if you put the numbers together, it's consistent with what we extracted for the Curie-Weiss temperature. And this energy scale is also in good agreement with this saturation field. So what's happening at the saturation field is that if you apply high enough magnetic field, you just polarize all the localized moments. So this is very consistent with the picture of a model insulator. So next, I would like to talk about how to use such a system to study the Mott transition I mentioned, right? And so in this picture, U is very big. That's why we see a very small antiferromagnetic interaction. So if we can make the ratio of T over U bigger, then we would expect to see, the energy scale to change. And this is what, we would like to do. And partly, as I mentioned, Mott transition is still kind of a mystery to us. And from experimental point of view, that's something not easy to study because it's not easy to find a system that you can tune the relative importance of interaction, the U over T. Often, people use doping to change that, but when you change doping, you can get into defects, because you need really reduce the density quite a lot. So you get into the limit of how clean your sample is, this and that. Some related study will be, pressure induced the bandwidth change. But, this will be one of cleanest system you can study, more transition. So let me just tell you a little bit about this combination. So I already switched the combination from WSE to WS2 to moire telluride. And the reason is because, moire telluride has smaller band gap. We can do electrical contacts better. So again, the device structure is very similar to what I showed before. But now in this case, we are going to apply electrical field while fixing the doping density in the moire to be 1. So we keep the doping density at 1 particle per moire unit cell, but then we continuously change the outer plane electrical field. So what this outer plane electrical field does is to change the relative potential difference between those two layers. Basically, you are changing the band alignment. And when you do that, you will change the hopping between the two layers. And that's one of the important factors that determine the depth, the potential depth here. So when you make your potential narrower, it's much easier for electron to hop from one side to another. So T will change exponentially. And U will also change a little bit, but much slowly. So the main effect is make a T much bigger. So when I tune the outer plane electrical field, I tune my bandwidth, so make this guy goes down, basically. Okay, so let's just take a look at some measurements. So again, what I'm showing here is the resistance as a function of a temperature for some range of electrical field. So each curve has fixed electrical field. So when I cool down the sample, resistance goes up. And this is very typical insulating state, right? And that's something we saw before, we have a more insulator. So you need to overcome a very large U energy in order to make this conducting. And if I tune the electrical field, increase just a little bit, and I got something very different. Now, instead of resistance going up at low temperature, now resistance drops. And if you look at the behavior at a very low temperature, the resistance goes up at some constant plus T square. And we like the T square dependence because, for Fermi liquid, that's one of the signatures for Fermi liquid. So you can analyze the data a little bit better. You can also collapse all the curves into two groups, insulating behavior and metallic behavior. So now when we change the electrical field, we are changing the U over T ratio, right? On the insulating side, from the activation energy, we can extract the charge gap. So the gap size decreases when we approach this transition. And then you can see that, the charge gap drops from somewhere 30 millieV to very close to 0. So that's on the insulating side. And on the metallic side, I told you it goes like a T square. And the coefficient actually is inversely proportional to the mass in the Fermi liquid theory. And you can see that the mass sort of diverges when I approach this transition. At the same time, if I measure the Hall density, the density doesn't change. And of course, it becomes kind of a noisy, when we get very close to the transition, And that's, the contacts, how low density, the low, high resistance, you cannot measure those very well. But from the range we can measure well, density doesn't change. And on the other hand, we can do magnetic measurements. So what I'm showing you here again is the magnetic susceptibility. So the bottom line is that left and right looks like there's no abrupt transition. The magnetic susceptibility changes a little bit, but across this point, everything looks like a smooth, right? So then I change my temperature from something relatively low to something high. And I want to mention that, in this case, near those points, the magnetic interaction energy actually has increased quite a lot. It's on the order of 30 Kelvin. So if I cool down the sample to about 2 Kelvin, we're talking about only 5% of Curie-Weiss temperature. And I still see this smooth, transition. And that just tells me that I have not seen any sign of long-range magnetic ordering. So from this picture, we can see there's an abrupt change in this charge sector, right? So from the charge gap closes, and from this measurement, it just says the spin side of the story doesn't change. So and based on this, we can make the conclusion, likely what we observed is some kind of a continuous Moore transition. And that poses some challenges, how to theoretically describe a continuous Moore transition, So we have charge Fermi surface disappear abruptly at that transition point, yet the transition is continuous. There's no obvious symmetry breaking, and this is beyond what we learn in phase transition, right? So one candidate is something like a charge spin separation. You can separate the charge and the spin, and the Fermi surface for charge abruptly disappear, but for the spin it stays. I'm not going to get into the details of this. And there are some other numerical results saying that yes, this could be a continuous phase transition, but then near that transition, there's a gapped, this chiral spin liquid. So the bottom line is that near that transition, there's something exotic going on, some kind of a spin liquid. But what is the nature of that spin liquid, whether it's gapped or it's not gapped, we don't know yet. And if such a thing exists, how to probe experimentally, this is also a challenge. The community is working on this. So I'm not going to talk more about this. So I just want to get back to my pretty pattern. I would like to tell you a bit more about the other kind of interesting features we observe in this picture. So we talk about this guy, and this guy, this is just the band gap. So it's a insulator. But how about, something like 1/3, 1/2, 2/3, and even weaker ones. And turns out those are charge order states. And we did Monte Carlo simulation, and those are the patterns, that come out when we take not just the on-site Coulomb interaction into account, we also take long-range Coulomb interaction into account. So in this moire system, semiconductor moire system, not just the on-site Coulomb interaction is important, which prevents electrons to occupy the same site. The neighboring or long-range Coulomb interactions are also important, which will keep the charge far away from each other as possible. So for example, this 2/3, this guy, we have for example, a honeycomb occupy, and then the middle of that pattern, we have an empty site, right? And this state is a charge order state, and sometimes you can call it generalized Wigner crystal states. Wigner crystal, usually we talk about electron crystals without lattice, and we add the word generalized because now we have lattice. So the Berkeley group did this STM study actually to directly visualize the charge pattern. So what they did, because our samples, because those moire samples are embedded right in the structure, so they place a graphing layer at some distance away from the moire, and the charge puddles will be reflected on the graphene, and then you can do STM on the graphene and see the pattern. So for example, this is the pattern they collected when we have 1 particle per moire unit cell, and those red dots just to help you to see, where the charges are. So I would like you to focus on the 2/3, right? From the cartoon, we are looking for honeycomb occupy, so those are the bright ones. Those are the position you have charge, and then you have this empty black spot in the middle, and those are the empty site. So so those are kind of the real image, and just confirms, those are real charge order states. But there are also other states, if you look at them, for example, 1/2, 2/5, or 3/5. And you can see that they break the rotational symmetry of the lattice, right? So especially this 1/2 state, you have rows, So something like this can also be probed experimentally. So we did this very sensitive optical polarization image measurement. So the moire samples are inside the dashed frame, and we know the crystal orientation of the moire by doing nonlinear optical measurements. And we can also measure along which direction the rotation symmetry is broken, and the amplitude, how much it's broken, right? And you can see that, when you have those stripes, those are the lines tell us about the order, the direction. And then we have 2 different types. They are at the 90 degrees. And those 2 actually correspond to alignment with the lattice, like either rows or zigzag. And they also have domains. But more interestingly, this breaking of rotation symmetry, which we call the stripe faces exist not just at 1/2 or 2/3, 2/5, or 3/5. They actually has this huge distribution over the entire range of a filling factor, from somewhere like a little bit over 0.3 to a little bit below 0.6. And then when you warm up, they disappear. And that's the melting temperature of these crystals, and they are consistent with other optical measurements. So what we have actually, not just those striped crystals, we also have this liquid crystalline phase. Okay, so I would like to summarize, what we have learned so far using this triangular lattice moire superlattices. Our experiment and other experiments on different TMD combinations all observe this insulating state at a filling factor equal to 1. When we tune the bandwidth continuously, we observed this continuous mode transition here. It changes from insulator to Fermi liquids continuously. And at the fractional filling, there are those generalized Wigner crystals, and some of them also break rotation symmetry. They are stripe faces and liquid crystals. So I probably will just say a few words, and I should wrap it up. So far, I just talk about how to make strongly interacting fermions. In this case, will be an electron, right? Then you may ask the question, can you make bosons strongly interacting on lattice? And this could be done. And if you think about this, the implication from theoretical point of view, people have already thought about this, and on the experimental sides, we are a little bit behind. But you can think about one way to realize something like this. You say, okay, if I can make two identical moire lattices, and I can place them very close to each other, and I can make sure that the tunneling between those two lattices to be negligible. And then if I can populate one moire lattice with electron and the other moire lattice with hole, then the strong electron hole interaction can form excitons, and then each will occupy some lattice site, right? So in this case, I will have strongly correlated excitons, which are bosons on a lattice. Right? This is something you can imagine very difficult to do, particularly to put electron on one lattice and a hole on the other lattice, because you need to find appropriate material with the right band alignment, this and that. But you can work with something slightly different. So let's say if I can make two identical moire lattices and I still put them very close to each other, but I can only populate one of the layers. Let's say I put an electron on the top layer. Then I'm going to apply an outer plane electrical field, which can push some of the charge from the top layer to the bottom layer. So for example, in this case, if the Coulomb interaction is very strong, then this charge on the second layer will be strongly bound to the empty hole left behind, because if I move to the next site, this Coulomb repulsion between this guy and that guy would be so strong. And this has high price to pay, right? So then I can think about the hole left behind and the electron in the other layer are an exciton pair, right? So that's another way to realize strongly interacting exciton on a lattice. And it turns out that even if one layer does not have moire lattice because of the very strong Coulomb interaction, if you push charge from here to here, they would like to stay very close to the empty hole left behind. And we also have kind of a related work when we put electron on one sheet and the hole on the other sheet, but they do not have lattices. So unfortunately, I don't have time to talk about those results, so there being some recent progress along this line, so you can also study strongly interacting excitons on a lattice. So with this, I would like to summarize. I'm not going to bore you with the details. The take-home message is that semiconductor moire materials are a unique platform to study model many-body Hamiltonians with highly tunable parameters. And we've seen interesting correlation many-body states. And so far, not, I would say, so this kind of the beginning of discovering new states, and it's kind of on the early stage. And magic, I think, is still coming, and this is a very fruitful direction for quantum matter physics. Let me put that way, okay. I would like to thank the people behind the work. First of all, Professor Kim Van Mack, who co-supervised the group with me, and the formal postdocs who contributed to the topics I mentioned. And those are the graduate students, who contributed to the topics I mentioned. And we have collaborators, both in theory and collaborators who grow high quality tungsten selenide samples and hexagonal boron nitride. So you can read their names here. So I stop.